So today's experiment we are going to see about cascade control system. Okay. So the cascade control system, how the question paper will be given. Okay. So here the problem will be given with G primary, okay, and G secondary. The total transfer function will be divided into two, and it will be given as G primary of S and G secondary of S. So இங்க வந்து G primary of S 1 by 5S plus 1 கொடுத்திருக்கோம். G secondary of S 1 by 0.1 S plus 1 into 0.3 S squared plus S plus 1. So total process பார்த்தா என்ன வரும் அப்படின்னா 1 by 5S plus 1 into 1 by 0.1 S plus 1 into 0.3 S squared plus S plus 1 தான் டோட்டல் ப்ராசஸ். பட் நம்ம கேஸ்கேடுக்கு இப்படி ப்ராசஸ் பிரிச்சிருக்கோம். ஓகே. ஸோ இந்த ப்ராசஸ் வந்து ஸ்லோ ப்ராசஸ், இந்த ப்ராசஸ் ஃபாஸ்ட் ப்ராசஸ் அண்ட் கம்பேர்ட் வித் ஜி பிரைமரி. ஓகே. இதை வந்து நம்ம இப்போ டிசைன் பண்ண போறோம். இதுக்கு நம்ம கேஸ்கேட் கண்ட்ரோல் சிஸ்டம் டிசைன் பண்ண போறோம். ஓகே. ஸோ ஃபர்ஸ்ட் இந்த டிசைன்ல நம்ம என்ன பண்ணணும் அப்படின்னா நம்மளுடைய இதுல ஃபர்ஸ்ட் வந்து செகண்டரி ப்ராசஸை டியூனிங் பண்ணணும். ஸோ செகண்டரி ப்ராசஸ் இங்க நம்ம கொடுத்துருக்கிறது 1 by 0.1 S plus 1 into 0.3 S squared plus S plus 1. இதுல இதை வந்து நம்ம மேனுவல் அது தியரிட்டிக்கலா பண்ண போறோம். ஓகே. we can do it simulation also, but it will be time consuming, so we are going to do it in theoretical approach. Okay. So we have to write the characteristic equation. The characteristic equation is given by 1 by 1 plus G of S H of S is equal to 0. Here H of S is taken as 1. Okay. We are considering the feedback loop is with a gain of 1 and the feedback loop is 1. Okay. The transfer function of the feedback loop is 1. So it is H of S is equal to 1. Okay. So while writing in this general form, we have to replace 1 by K. That is the numerator terms by K. So it will be 1 plus K divided by 0.1 S plus 1 into 0.3 S squared plus S plus 1 equal to 0. Okay. Now you multiply all this thing. You take LCM and this denominator term on cross multiplication, it will become 0 because it will be getting multiplied with 0. So it will be 0. Okay. So on simplifying this equation, we will get 0.3 S cube plus just this multiplication. Okay. Plus 0.4 S squared plus 1.1 S plus 1 plus K. Okay. Clear. So is equal to 0. Okay. Is this K. Okay. This is equal to K because all this term on taking LCM, it will come to where? So all these terms, it will come to this part. Okay. All this term will come here. Okay. All will come here, and this the denominator will be cross multiplied on the other side, will become 0. So you will get this equation on simplification. Okay. Right. Now you apply Raoult criteria. I'm recalling the same equation. Okay. Whatever we have got here, this equation is recalled in the next slide. See, the Raoult stability analysis we are going to do. So 0.3 S cube plus 0.4 S squared plus 1.1 S plus 1 plus K is equal to 0. So first you write the odd terms. Okay. So S cube is the highest power. So you write S cube. So 0.03 is the coefficient of S cube. And then for S, okay, odd powers you write. So it is 1.1. Next you go to S square term, even powers. So S square. So for S square it is 0.4 and the constant is 1 plus K. Now you find the Raoult multiplication. You do the Raoult multiplication and you find S1. Okay. Cross multiply and divide by 0.03. Okay, I think you will be knowing this. So 1.02 minus 0.075K 0 and S naught, it will be 1 plus K. We don't need S naught, just for completing the task I'm doing that. Okay. Now you equate S terms to 0. Okay. The S terms means S power 1 terms to 0. Okay. So here you have only 1.02 minus 0.075K. Yes. Other term is 0 here. So it's just equal to 0. Okay. So here 0 point, so S term is common, okay, S term is common, so you remove it, okay. So 0.05, you bring this 0.05 to other side, so it will become 0.0507, 0.075, k is equal to 1.02, so k is equal to 13.6. This is the ultimate gain, okay, this is the ultimate gain, 13.6. That is, we are calculating the ultimate gain and ultimate period, okay. So we are going to tune the secondary process using Ziegler-Nichols closed loop tuning method, okay. So for that, this is the theoretical procedure to estimate the ultimate gain and ultimate time period, okay. Now you equate S squared terms to 0, okay. So 0.4 S squared plus 1 plus k is equal to 0. In this, in the term of in the S terms, you put j omega. So it will become zero point 0.4 j omega into plus 1 plus k is equal to 0. Okay, you put the value of k, okay, for in the place of k, in the place of k, you put the value what you have got here for ku, okay. So here the equation will become 13.6, 0.4 omega squared into plus 1 plus 13.6 is equal to 0, okay. So here they will become 14.6, 1 plus 13.6, it will become 14.6. You simplify, you will get omega is equal to divided by zero point 0.4, because when it comes to other side, and other side, uh, minus minus get cancelled, and 14.6 divided by zero point 0.4, and then you take square root, you will get omega is equal to 6.04. Okay, now you substitute omega. Omega is nothing but 2 pi f. Okay, you substitute over omega as 2 pi f. So 2 pi f is equal to 6.04. F is equal, now you find f, you divide 6.04 by 2 pi, and then from f you calculate t, okay. T is equal to 1 by f, so it is 1.04. pu is 1.04 seconds, okay. So now you can decide what controller you can put for the secondary loop. You can go for p loop or pi loop, okay, proportional mode control action or pi mode of control action. Generally for secondary loop, these two controllers are preferred, and in our process we are doing for only for p control. So for implementing only p control, this term is alone enough, but to have a knowledge about how to calculate pu, I have derived here. Suppose if you want to go for pi mode of control action, this procedure you have to use. So to knowledge you, I have given this, okay. Right. So secondary controller, we are going to put it in P mode, as I said earlier. Okay. So in P mode, the Ziegler-Nichols controller setting is Kc is equal to zero point 0.5 into Ku. So it is zero point 0.5 into 13.6. So Kc is equal to 6.83. Okay. So now we have designed the secondary controller. We are going for the design of primary controller. So before going for design of primary controller, the primary controller, here how we are going to design, we are going to use Cohen-Coon tuning method. Okay, we are going to use Cohen-Coon tuning method. But the secondary transfer function should be in closed loop. The secondary transfer function should be in closed loop. So how the block diagram is formed in MATLAB. So see this here, this is the secondary loop. Okay. So this is the secondary loop with feedback. Okay. Clear? Okay. So 0.1s plus 1 into 0.13s square plus s plus 1. It is given by proportional controller. So I am putting a gain block. Proportional controller is nothing but a gain block. So here in this the gain is implemented as 6.83. Okay, the gain is implemented as 6.83. Okay, 6.83. Okay, which we got in the previous calculation. Okay, which we got in the previous calculation. Okay, here we got no that calculation. Okay, 6.83, that value I'm putting. Okay, right. So you can see in the previous one. See here we have got 6.83. So that one is implemented. So the secondary is in closed loop. Now I am adding the output of the secondary. I am not giving directly to scope. It is getting connected to the primary. Okay, it is getting connected to the primary. Okay, and the primary output is given to the scope. The scope is not needed. Okay, so this scope is not needed here. Okay, you forget about this scope. only this scope is needed. Okay. Uh, on, so here uh, a scope is connected and you are going to find a shape curve. So a unit step response is needed. So for that I'm putting unit step input. Okay, clear, right? So what I will get? I will get a shape curve. Okay, I will get a shape curve like this. Now from this S-shape curve, I'm going to do calculate all the parameters. Okay, uh, so K, tau, TD, and I'm going to find the model of the process. Generally, or the cascade control or any controller, we will be any control mode we will be using PI control of action. So for primary controller, I'm going to use PI mode. So I do only the PI controller settings of Kohn tuning. Okay, I'll find the KC and TI value using this. Okay, clear, using this formula, and from that I will find the closed loop. Okay, so this is the response, actual response, which I will be getting or you will be getting when doing this example. Your S shape curve will be like this, and for this you calculate the 0.8723 is the gain. Okay, here it will not settle in 1, right? Okay, previously we are speaking, no, it will settle in 1 because the input is 1. Why it will not settle in 1? Because here you have a closed loop. Okay, here you have a closed loop condition. Okay, so even though you give 1 as the input, the process will not settle at 1. Okay, clear. So the maximum value, it will be settling at some other value, so 0.83. So to note down that, you have to give 1 meter here. Okay, you have to give 1 meter. Okay, we'll do in the MATLAB. At that point I will tell. So 0.83, it is settling at 0.83. So the gain is now not 1. So it is settling at 0.8723. Okay, so final value minus 0, initial value 1 minus 0. Okay, input. So your gain is 0.8723 and T1, T2 are noted. So from that you have calculated tau TD. Okay, now the process is modeled. Okay, K e power minus TDS divided by tau s plus 1. You will get the equation like this. Okay, right. Now the tuning model is obtained. You implement in the formula, find the value of Kc and Ti. So what you are finding is Ti. In MATLAB, you have to implement as Ki. So 1 by Ti is your Ki. You know the formula we have studied in process control. So 1 by 0.75 is 1.32 second inverse. Okay, right? So with this, the design of Cascade is getting completed. Okay, so now we are implementing. Okay, already the secondary loop was implemented. So here we have implemented the gain as 6 point something. I don't remember correctly, 6.83 I think. Okay, so here uh, in this primary controller you implement P mode KC as what, 20.1, 20.1 and 20.1 and KI 1.32. Okay, KI is 1.32. Okay, KI is 1.32. Okay, see the structure of the cascade loop. So it is similar to the one you have studied in your theory. Okay, right? So there is a secondary loop. This is the secondary loop. Okay, and you have a primary loop. Overall loop is primary loop. So the primary output is taken and given to the master PID controller. Okay, here you have a set point, and the set point, the output of the primary controller is given to the secondary controller as set point. The output of the secondary process is given for comparison to the error detector of the secondary controller, and you have a proportional controller here. Okay, so this is the entire scheme which we are going to do. Okay, which we are going to do in MATLAB. Okay, right? So with this, the first part of the experiment is getting completed, right? What is the second part? We have designed a cascade control scheme. Okay, now I have to prove that this control scheme is better than the Conventional control scheme, that is without any secondary loop, the control scheme without any conventional uh, இது controller, okay, secondary controller. So for conventional controller design, what I have to do, I have to merge all the three process, all the three diagrams, okay. So you merge all the things, primary transfer function, secondary transfer function, you give a step, okay, you will get a S-shaped curve. So again you repeat the same procedure, okay, you will be getting a transfer function, okay. Now you use Cohen settings, again you have to choose PI mode, okay, you choose PI mode. So this is the tuning, okay, how you will get the response, a shape curve, okay. So in the tuning response, okay, you see tuning of PID, for conventional control scheme. So in this it will settle at 1. Here it will settle at 1. Why it is settling at 1? Because there is no feedback here, okay, because there is no feedback for secondary loop here. The secondary loop is in series with primary and it is open, okay, it is not a closed loop. So you will get 1 as the final value, okay. So do it, right? You find the controller settings T2, T1, tau, TD, model the process. You good, you give PI control action formula, you find value KC 3.30 and KI 0.157 seconds inverse. Okay, now so already we have done the secondary control scheme, you implement the primary control scheme, okay. So only one PID, you compare them, you give it to a mux, okay, multiplexer, you connect both the output and give it to a scope, so you can see the comparison, okay. So the response will be like this, see, the conventional control scheme and the cascade control scheme. The conventional is in dotted line, cascade is in solid line. You can see the solid line settles earlier, okay, and with minimum overshoot, there is no undershoot, almost no undershoot, there's a little undershoot, okay. So it's a little bit undershoot. So this cascade control scheme proves that it is efficient than the conventional control scheme and it makes the process to settle earlier, okay. With this your experiment is getting completed, okay. Now we will go to MATLAB, okay. So the problem will be given like this. We are going to tune secondary using theoretical approach. The theoretical approach is route. So in the route, you have find the P mode control action. Now we are going to do tuning of primary controller. Okay. So tuning of primary controller we are going to do. So you open MATLAB. In the MATLAB you open Simulink. You go to home, click Simulink, it will take time to open, and then you click new file, okay. So in that you form the blocks, okay, you form the blocks as like this, okay, you form the block as like this, okay. So here I think I have already formed the blocks, okay, right. So I have formed the blocks. So two-dimensional array. See, I am going to simulate. See, it is in closed loop. I have to check whether the gain is implemented. Yes. So the gain here is implemented as 6.83. Where I got this using the theoretical approach. This gain I have got 6.83. I have got, okay. So this value I'm implementing there. Okay. Okay. So 6.83. Just you double click, there will be some value there, you enter 6.83 and you click OK. Now you run the process, okay. So it's getting it 7.5, so you increase the time to 100 or you increase it to 1000, okay, what's wrong? So 8723, okay, you check again whether it is getting settling. After that you add 10,000, 10,000, run again, it is getting 0.8723, you make it 1 lakh or more than that. Again it is 0.8723. Okay, right? Okay, so the final value is 8723. Using this display, we can find. Without display, it will be difficult. So add a display. Okay, in the block diagram, I have not shown the display. Okay, here I have not shown the display. So you add the display. Okay, right? Okay, so you can see the graph there. Now, okay, so primary after finding the S-shaped curve, so you'll be having a S-shaped curve. See, auto scale. Okay. So something is not strict and finally everything is good. Mm, okay. So we'll go to the figure and we will see there primary tuning. Plot primary tuning. Okay, so it's very long time we have simulated. That is the mistake here we have done. So make it as 150. Okay. Now we will see the response. See now it's getting okay. So even at okay, so it is a shape curve. So now, so run it for smaller time. Okay, even 150 is more. So you make it 75. It's enough. As it is setting 0.8 or 50, we will try. No, for 50 it's not coming. So 75, it is coming at final value 8723. Okay, so it takes 75. Scale. Okay, see the shape curve you are getting. Okay, again you do 6.632 value. Okay, and after that you do for 0.283. Okay, for 0.283 you do, you find the values, and then you calculate the gains. Okay, so you calculate the gain. Okay, right? So see here, I have shown 0.8723. Okay, 8723 minus 0 divided by 1 minus 0. Okay, in the output calculation. That is the thing. Okay. Now I think you can understand why I are getting, because here we have a closed loop. Because of that, the value is getting changed. Okay, right. So now you find the primary control tuning and you implement the cascade control. Okay, you implement the cascade control. So now this is the cascade control scheme. So in the cascade control scheme we have to implement the gain values. So what are the gain values we have found? So using this formula we have found the gain values as 20.1 and 1.32. Okay, so you make proportional gain 20.1 and integral gain as 1.32. Okay, 1.32. You give okay. No other thing you should change. Okay, you should not change anything. Okay, so now you go for primary tuning. Okay, so cascade control is designed. Okay, so this is the cascade control scheme. The cascade control is designed, and to see the output we have put a separate scope, a workspace block and a display. Okay, right? And we have also connected to the mux. So where to take the mux? So mux can be taken from continuous. Okay, mux, sorry, commonly used block, you can have the mux. Okay, here it is. See, you can use that mux, and in the gain block you can see in continuous. Okay, if it is not available in continuous, go to math operation. There you can see the gain block. Okay, so this gain block is used in the place of secondary controller. This gain block is used here. Okay, right? So here you see it is 1. So here I type 6.83. It will come. or 6.1, like this my example, for example. ஓகே, ஸோ இந்த மாதிரி மாற்றிட்டிங்கன்னா உங்களுக்கு வந்துடும். ஓகே, நெக்ஸ்ட்டு இப்போ நம்ம கேஸ்கேட் கண்ட்ரோல் முடிச்சிட்டோம். ஸோ கன்வென்ஷனல் கண்ட்ரோலோட இது பெஸ்ட்டாக இருக்குன்னு நம்ம பண்ணணும். ஸோ அதுக்கு கன்வென்ஷனல் கண்ட்ரோலர் டிசைன் பண்ணணும். ஸோ கன்வென்ஷனல் கண்ட்ரோலர் பண்ணோம்னா செகண்டரி லூப் எடுத்துடணும். ஸோ செகண்டரி லூப் எடுத்துட்டா நமக்கு இந்த பிளாக் அப்படியே 3 சீரீஸ்ல வந்துடும். செகண்டரி லூப் இருக்காது, ஒரே ஒரு கண்ட்ரோலர் தான் வரும். ஸோ அப்போ இதுக்கு நம்ம கொஹன்கோன் டியூனிங் மெத்தட்ல கண்ட்ரோலர் செட்டிங்ஸ் கண்டுபிடிக்க போறோம். ஓகே, ஸோ அது எப்படி கண்டுபிடிக்க போறோம் நம்ம ஏற்கனவே டிஸ்கஸ் பண்ணோம். ஓகே, இது மூணையும் ஓப்பன் லூப்ல வச்சுப்போம். கரெக்டா? ஓகே, கன்வென்ஷனலுக்கு மூணையும் வச்சு ஸ்டெப் இன்புட் கொடுத்து அவுட்புட் பார்த்து நம்ம கண்டுபிடிப்போம். இங்க ஒன்ல தான் செட்டில் ஆகும்னு நான் சொன்னேன். ஓகே, இந்த மாதிரி உனக்கு எஸ் ஷேப் கர்வ் வரும். ஸோ நம்ம பிரைமரி நம்ம டியூனிங் இருக்கு பார்ப்போம். ஓகே, ஸோ கன்வென்ஷனல் லூப் டியூனிங் பாருங்க, 3 பிளாக்கும் இதுல சீரீஸ்ல போட்டிருக்கேன். ஓகே, சீரீஸ்ல போட்டு ஐம் கோயிங் டு ரன் திஸ். ஸோ 0.829 தான் வருது, நமக்கு 1 வரணும், இங்கே ஃபீட்பேக்கே இல்லை. ஸோ 25 or 30 we will make. Okay, even then it's not coming. So 100 we will put. Okay, 100 is coming, so we'll check for 75 or 80. Okay, so right now you see the graph, it's a shape curve. Okay, so it's a shape curve. Clear? So, see, and now again you complete 0.632 and again you do for 0.283. Okay, so you calculate, okay, everything, and you find the PI control action. So you'll get 3.30 and 0.157. Okay, so this one you implement in the cascade controls scheme. Okay, what are the values you have got? So 3.30 or 0.157. So in this PID you give 3.30 and what is the value? 0.157 integral. 0.157. Okay, okay, so for both you give the same set point. Okay, so for both you give same set point. You can give set two separate, but you have to give same value. Okay, so step time it should be 0 initial value, initial value should be 0, final value I'm giving a set point of 15. Okay, right, now you run it. There's something wrong. So we'll try with some lower gains. Okay, so for 150 it is not settling, so 200 we put. Okay, so 200 it is both are settling at same point. So you check this calculation may be wrong, so I have reduced the gain. Okay, see auto scale. Okay, there is a difference. Okay, so this is the cascade one, and the conventional one we will see here. So see, it is taking more time to settle. Okay, so here in the comparison, so this is the comparison. Okay, you go to MATLAB main window, select T out. So here we are given two things, conventional and cascade. Okay, so you have to select those things. T out, first one you have to select T out, and next is conventional, Next is cascade. See, the array size will be same. From that you can differentiate. Okay. If many blocks are with the same name, you can differentiate with that. So 74 into 1, 74 into 1, 74 into 1. First select T out and then select all the other things. Okay. You right click on T out. You plot. You select plot as multiple series versus first input. Okay. Clear? Right. So you have the graph. See how it is settling. It is taking more time. Okay, so you put insert legend. Okay, so the red is cascade, it sets settles earlier. Blue is pi, it settles later. Okay, so with this your experiment is getting completed. Okay, so complete it. So you can edit the graph using usual procedure. Okay, in the previous experiments I have shown, follow the same procedure and you complete the experiment. Okay, thank you all the best completing the experiment. Thank you all the best.